Hello, in the past videos we discussed about greedy algorithms and some questions. Let's discuss the next one. Here is the question, read it and give it a try. An aspiring programmer is gearing up for upcoming Women's Cup coding competition. We have to return the minimum number of operations required to make all integers of the array given equal. In one operation, one can flip any bit of any element of array. Considering the given array, in one operation, we can flip any bit of any number and we have to find the minimum number of operations to make all elements equal to any number. So for example, if the array is 1 and 2, and if we try to flip the first bit of 1, it will be 1 1, and if we try to flip 0th bit of 2, it will be 1 1. So we have made final value equal to 3 both. So the minimum number of operations are 2 to make all elements equal. We have to return that number of operations that we are doing. So the size is up to 105 and the value is up to 109. So the question asks us to find the minimum number of operations to make all elements equal, so that in one operation any bit of any number can be flipped. Let's assume that we also have to find any final value that all are converted to, and if there is only one value, return it, or if there are many multiple values, return any of it. So what is the first idea? So we have 1 in 9 possibilities because the numbers are up to 1 in 9. So we have 1 in 9 possibilities of final answer to make all elements equal to x. So try for all values x. So for example, let's start from 0. And what are the minimum operations? What are the operations to make all elements equal to 0? So, and similarly, we can find what are operations required to make all 1 and so until all the numbers. So we can return final minimum value. So let's say for an x is equal to 3, we have to find answer for 5. So it is 5 in the binary. So what are the minimum, what are the number of operations to make 5 equal to 3, so that in each operation we can flip any value. So the 5 is 0 1 0 1 and 3 is 0 0 1 1. So how many bits we have to flip? So it will be 3, it will be 2, because we can flip 1 to 0 and 0 to 1, because 0 1 both are same in both. So it is simply set bits of XOR, because if the values are 0 1 and 1 0, we have to flip, and XOR of these both is 1. So if they are both are equal, XOR is 0 and no need to do operations. So simply if we are trying to make 0 to 1, the number of operations equal to 1 and XOR is equal to 1. So the number of operations is simply XOR of this. So as there are multiple bits, we want total count. So simply it will be set bits of XOR. So it will be 2 here. And what's the time complex of this? It will be 1 in 9. It will be at least 1 in 9. And we have to traverse all the loop as well. It will be into 1 in 5, which is very hypothetical. So let's try to optimize this. Do we really have to try all the values for 1 in 9 values? So in the before brute force, we are trying to traverse all the values from 0 to all. Is there really a need? So let's assume we have only 0 and 1 in the values, because we have binary numbers and they can go up to 2 power 30, because it's the highest bit that can be set in 1 in 9. So let's assume that we have only one bit, and let's think of this bit. So let's assume we have 3 zeros and 4 ones. So obviously the final values can be 0 or 1 only, because we are dealing in binary. So it can be 0 or 1. So what are the number of operations required to make all values 0? It will be number of ones, because we have to only convert ones to zeros in one operation. So it will be 4, because we have 4 ones. So to make all values 0, it will be 4. And what are the number of operations required to make all equal to 1? It will be number of zeros, because we have to flip zeros to make ones. So it will be number of operations are 3. So we have to return the minimum number of operations. So it will be minimum of ones and zeros, because to make 0, our answer are number of ones, and to make ones, the number of operations are 0. So final answer is 3, because this is the minimum of both possible choices. So it will be minimum of ones and zeros. So we got an answer for 1 bit, because we have many bits. We got answer for this because these are 0 and 1, and this is the exact case. So we got answer for 1 bit. So let's say we write the given numbers in binary, as we got answer for 0. So if we assume that these 5 are the 5 values, and let's say we are dealing with highest bit, and there are 2 zeros and 3 ones, and similarly all. So what are the minimum number of operations to make these equal to any of these? It will be minimum of these both, as you have seen here. It will be minimum of both, and here minimum is 2, 2 and 1. So we got the answer for every bit to make all values equal. So is the final answer sum of all these? Because we got answer for last bit, for last 1 bit, last 2 bit, and so on till 0th bit. So is the answer sum of all these? The answer is yes, if they are independent. And are they independent? Surely yes, because let's say we have these values, and whether the values are 0 or 1 here or 0 or 1 here, there is no difference, because this bit is isolated into a single array, and this other bit is also isolated single array, and so on. So there is no dependence on this. Even if the values are 0, there is no difference of the next bit if previous bit is 0 or 1. So this is independence subproblem and this is input subproblem. So answer is simply sum of all this. So before going to this, let's check how to make this as well. So one left shift j is 2 power j. So how to check whether the kth bit is set in v of j? It is simply v of j bitwise and with one shift k, which is 2 power j. So if it is 1, it means the bit is set, and if it is 0, it means unset. For example, let's take 1 0 1 1 0, and we have to find whether fourth bit is set or not. So we are doing AND with 2 power k. So 2 power k is simply only that kth bit will be 1 and other all are 0. So it will be 0 1 0 0 0. So bitwise of two numbers will be 1 if both are 1, else it will be 0. So 1 and 0 is 0. We are coming bitwise, and 0 is 0 is 0, and 1 and 0 and 1 and 0 and 0 and 0. So this is 0. So it means that there is no at least one bit. For example, if the values are 1 1 0 and we are checking whether first bit is 1 or not. So and 1 left shift 1, it will be 0 1 1 0 1 0, and it will be 1, it will be 0 1 and 0, because before all values are 0 and after all values are 0, and 1 is same, so it will be 1. So it is not equal to 0. So it means that we have one bit which is set. So in this way we can check whether if it is 1 it is set, if it is 0 it is unset. So initially the number of bits can go up to only 30 because the numbers are up to 29, and we are looping through all numbers, and we are counting the number of bits that are set at all bits 0 to 30, and if the bit is kth bit is set, we are incrementing bits of k, it will be plus plus. So in this way we can find the number of set bits at all bits from 0 to 30. So finally we are traversing all bits to get answer, and the number of set bits is this bits of j, and the number of unset are n minus j because total are n, and if x are set, n minus x are unset. So we have assumed that we have to find the final value as well. So how can we find this final value? For example, let's say we have three values, 1 and 2 zeros. So obviously we are sure that we are going to make this one because zeros are less than ones, so we are going to make one. So what this means, so we are making the final value 1. So in the final answer, the number that we are converting at the bit is 1, because we have triple ones and double zeros. So we are going to make final value here 1. So in the final value, this bit is going to be z, because we got that we are going to make this in the final value. And for example, let's assume that the numbers are 1 0 0 1 and 0 1. So the number of zeros here are 2 and the 1 is 1. So surely we are going to make all these 0 because we have maximum 2. So it will be 0. And we have 0 1 1, and the number of zeros is less than 1. So we are going to make this one. So this is the optimal bit corresponding to this, and this is the optimal bit corresponding to this. As we discussed, these are independent. The final value will be 0. So the number of operations are minimum when we take final value 0 1, and the answer is 2 because it will be 2 minus 1 here, and minimum of 2 minus 1, 2 and 1, it will be 1. So if set is greater than equal to unset, it means that we are going to make that set, because set are maximum. So we are going to make unset into set. So that will be this, and we are going to make answer equal to min of set and unset as we have discussed here. So it is simply minimum of ones and zeros. So in this way we can return the answer, and we can return the one of the final values which we are going to make in the final to make minimum operation possible. So it is the same code. We are traversing the bits and counting the bits, and we are finding the number of the answer for, and we are finding the final number that we are making 2, and we are finding the answer, and we are bringing answer n. So in this way we can find the answer in of n log n, because log n is 30 here because the number of bits are up to 30. So in this way we can find the answer. If you have any doubts, comment below. See you in the next video.